Now I would like to show you a variation on the structure that we talked about. What was that structure? We had an normal distribution, and the population variance was somehow given to us, and then we conducted a hypothesis test on the population mean using that information. The most common thing that we are going to encounter in daily life when we would like to conduct hypothesis tests is we would not be knowing the population variance. So can we use standard, the sample variance, or actually sample standard deviation instead of population standard deviation? If you recall from the discussion, from our discussion on confidence intervals, there were actually two conditions for that. If n is large, and we have given the condition that n is greater than, sample size is greater than 40, yes, the population standard deviation term can be replaced by sample standard deviation term. And note that this can be done regardless of the form of the distribution of the population, which relies on central limit theorem. If you recall, we had two remarks or two relaxation of assumptions. The first one was a relaxation of the normal distribution of the population assumption. We can relax this assumption if n is greater than 30. X can be of any distribution, and if n is slightly more larger, let's say n is greater than 40, then you do not need population standard deviation. You can use sample standard deviation. So this is again going to be applicable for this case, since actually hypothesis test, the way that we conduct the hypothesis test using fixed significance levels and also using the confidence intervals, they are actually equivalent in terms of the result they find. Now, on the other hand, you may say, what if n is smaller than 40 and we have a normal distribution? And that is something that is the case that we have already covered when it comes to confidence intervals. What we call in this case the standardized sample mean value is, but the standardization is going to be performed through division by sample standard deviation, is going to be t-distributed. So it's going to be the same thing here. Let's assume that we have a null hypothesis in this form. Actually, we are going to be talking three cases again: case 1, case 2a, and case 2b, where 2a and 2b will the alternative hypothesis will be consisting of one-sided inequalities, where case 1 will consist of a two-sided inequality. But in null hypothesis is the same in all of these cases. So given that we have this null hypothesis, then our test statistic will be, so note that we would be given a sample of n element, n specimen, n observations. And from this sample, we would be obtaining x bar value and put that value here. Mu0 is going to be the value suggested by the null hypothesis. Now this value is going to be divided by, note that this is not going to be population standard deviation. Instead of that, we use sample standard deviation, which is going to be obtained from the sample. So find the sample standard deviation, put it here, divide by square root of n. The resulting thing is going to be, this resulting term is going to be t-distributed with n-1 degrees of freedom. Note that t-distribution is actually a broader version of normal distribution. So as n, the sample size increases, t-distribution starts to look like more and more to normal distribution. As n goes to infinity, you have t-distribution, which converts to n distribution. So here that sample size minus 1 is the degrees of freedom. So it's the very same, it's almost identical procedure. It can be seen here when we have a normal distribution with sigma unknown compared to normal distribution with sigma known case. But the only thing what changes is, instead of sigma, we write sample standard deviation, and the resulting sample statistic is going to have a t-distribution with n-1 degrees of freedom, not standard normal distribution. So again, we are going to be talking about three cases, and the only difference between those three cases, as I pointed out, is the alternative hypothesis, the inequalities in the alternative hypothesis. So we have covered this in normal distribution. The same is applied here. we are going to determine a critical value based on alpha over 2. So T alpha over 2 at n minus 1 degrees of freedom. This is going to correspond to, in two-sided t-test, is going to correspond to this point here. So if t0 value, the absolute value of t0 value, note that it may be also negative value, but we compare with either this one or this limit. Therefore, we are going to reject H0 if our t0 value falls here or here. And the p-value, well, this notation, as you can see, is different from the notation for normal distribution case, but it exactly corresponds to the same thing. Let me try to explain this notation. It's very simple again. If you recall, p-value is simply find where t0 is, for instance, t0, let this time t0 be at a negative point. So t0 is smaller than 0. Here, let's say, this is where t0 has come out. So in this case, p-value is going to be this area plus the negative of t0. Note that this is going to be already negative. Another negative sign is going to make this positive. Is going to be this tail. And note that they are going to be both a, the same. So it's going to be equal to, p-value is going to be equal to 2 times a. This is how it's going to be computed. So the way to compute is, this absolute value of t0 is going to always make this automatically here. So instead of minus t0, I could have also written here absolute value of t0. So it says that find the t distribution value for n minus 1, which is greater than this t0 value. So the corresponding probability here is going to be the probability that is stated here corresponds to this area. I'll try to repeat again. This probability means actually t0 is going to be always here in absolute values under t distribution. Find the values of t distribution with n minus 1 degrees of freedom, which is greater than this part. Find the corresponding probability means find the area here and multiply by 2. The reason why this is shown in this representation compared to normal distribution is due to the difference in the resolution of normal distribution and t distribution tables. If you recall from your textbook, the t distribution table is much less focused compared to normal distribution table. Its resolution is much lower because we have all degrees of freedom, different degrees of freedom. So if you would like a t distribution table having as much resolution as a normal distribution table, then it would have taken pages. All right, so case A is then the inequality turns into mu is greater than mu0 value. Then this fixed significance level approach is going to consist of an upper limit evaluated at t alpha. Note that it's not going to be t alpha over 2, but it's going to be at t alpha. The reasoning is, I think, obvious. And the p-value is going to be exactly equal to this, but it's going to be one-sided. There is one more interesting point here. As you can see, there is no absolute value here. And I think there's a question in one of the exercise question or assigned question I'm going to be giving you. That's an interesting thing. Now, this simply means this. Find the t0 value. Let's say that it is here, and it is actually this area that we are talking about as the p-value. So t at n minus 1 degrees of freedom. Find the t values here which are greater than t0 and find the corresponding probability. However, there's an important difference between this one and this one. This one is an absolute value, therefore it's going to be always on the right-hand side. On the other hand, this simply says t0. So actually, this t0 could have been easily here. So this corresponds to, in that assigned question, I think it's going to be much more clear. Since you haven't solved it yet, it's going to be a little bit abstract here. But maybe after you solve the question, you may watch this video again. This t0 value is going to be on the left-hand side of the average value. Therefore, it's going to be t0 is equal to x1 minus u square root of x. And This means that X bar value is smaller than mu value. So you suggest, for instance, mu to be equal to 50, mu is greater than 50. This is your alternative, null and alternative hypothesis, but your X bar value comes out to be 48. Now, without any hypothesis test, with just using your common daily life rationale, think about it. You would like to show that as a research question, as an opposing hypothesis. You suggest that mu is greater than 50, but the sample mean, the mean that you have obtained from your sample is 48, is even lower than 50. On the other hand, hypothesis tests were really about, well, X bar is probably greater than 40, but is that much, is the amount that is greater than 40, is it significant enough so that we are going to deem the null hypothesis to be incorrect and the alternative hypothesis to be correct? Well, actually, it is on the left-hand side. So, is for this case, any person with a rational mind should not consider, would not consider the alternative hypothesis to be true. So, in this case, p-value should be a pretty much large value. So, thinking about that, actually, p-value in this case, and it's going to be where t0 value is, because this is going to be where mu is. It's going to be standardized version of mu, which is going to be 0. So 48 is going to fall here, which is the standardized version of 48. P-value is going to be this right-hand side probability. Now, if you look at in this equation, it exactly says this. So it says whichever value of t0, whichever sign of t0, it doesn't matter. If it's positive, positive. If it's negative, again put it here or here under the t distribution. You always compute this right-hand side tail area for this alternative hypothesis. On the other hand, this is different. And for case B, it is just the opposite. It's the very same thing, but this time we are talking about the negative numbers here. So it's going to be minus T alpha, and the p-value is going to be equal to, now note that again, these are again taken as T0, but the left-hand side is taken. So therefore, if we are talking about, for instance, here, the t-0 value has come to be here, it's going to be this probability. If it has come to be here, so we say that the alternative hypothesis mu is smaller than mu0. However, the sample mean has come out to be even larger than mu0. Still, this is going to be the area. But note that p-value is going to be very high probability. And the high probability of p-value means that it is very highly unlikely that we would be able to reject the null hypothesis. All right, now let's solve a question. Molar concentration is the quality variable in a chemical product. All right, we produce a chemical and we are interested in each of our products is molar concentration, and we know that it is normal distributed. All right, what we would like to test is whether the mean concentration of all the products that we produce, that all of these products, right, and we obtain x bar x to all of these to infinity or more, a very high number, from in this distribution, the population mean, whether this exceeds this 0.020 or 820 moles or not. And we would like to test this hypothesis at a significance level of 0.05. So the very first thing that we are going to do here is, of course, we are going to start with a hypothesis test. So H0, the null hypothesis, will be, as always, inequality. And the alternative hypothesis here, since it says we would like to test whether mu exceeds, so it's going to be, mu greater than moles per liter. And we are going to conduct this test at 0.05 significance level. All right. Now, at this point, since this is a one-sided test, and if we go back, for one-sided test, we would like to do this comparison. and the compared value is going to be the upper control, the upper critical value is T alpha n minus 1. So here this is going to be equal to, it's very difficult to find the cursor here, T 0.05 n minus 1 is, now here is the important thing, as I said earlier, although we haven't taken the samples yet, we have to determine the sample size. So actually, let me also give that information. We are going to use a sample of 15 observations. Let's not see the samples yet. So we are going to conduct a test on 15 observations. So it's going to be 15 minus 1, T 0.05 with 14 degrees of freedom. This is the value that we need to find. And this value is 1.761 that we read from our textbook. So this is going to be our upper critical value or limit. And we are going to test whether T0 is greater than this upper critical value or not. Now the question is, what is this value? To obtain the T0 value, we collect a sample of 15 observations. And these are the 15 observations. I have written only of those two, right? And then using this observation, of course, in a real question, all of these values would be given to you, or in a real life situation, you would be collecting these data by yourself. And then from that data, you are going to determine X bar and S. Just to give you the idea here, that focus on the, not the mathematics, but the focus on the procedure, I skipped those steps. So X bar is found to be from that sample is equal to 0.837, and S is given with that value. First of all, let's not go over any of the topics blindly, but let's not also go over this hypothesis test blindly. What was the idea here? Well, the status quo was mu, it is believed that mu is equal to 0.82 or 820. On the other hand, there is some suspicion that, or there's a feeling that, or there's a controversy that mu may be greater than that value. And when you take a sample of 15 observations, this is the X bar value. First of all, X bar has come out to be greater than 0.820. Now, this shows that we may be on the right track. But the question that I repeat again, the hypothesis test is trying to determine is whether that 837 compared to 820, whether that deviation is due to only sampling variance, or we may say due to luck only, due to just random noise, or due to the fact that mu is greater than that value. And this will all depend on the population variance. And since it's not given here, this is going to be determined by sample standard deviation, or it's going to depend on the population variance for which we are going to use an estimate using sample standard variance. So here we have already found S actually. Now let me get rid of these. T0 value here is going to be equal to X bar minus mu. So mu 0 S over square root of n. So X bar is 0.837 minus, where is mu value? Let me write the hypothesis test here again. All right, divided by standard deviation is 0.0246 divided by square root of 50. And the obtained value is 2.72. And we had already found at the very beginning, we had found this value, this upper critical value as 1.71. So when we compare these two values, T0, which is equal to 2.72, okay, this is greater than T0.05, 14, which is equal to 1.71. This means that, therefore statement, there is evidence to suggest that mu is greater than, well, actually, even instead of mu, it's better to write the whole description of the process. The mean molar concentration is greater than 0.20 moles per liter. Now note that this conclusion is obtained at a significance level of 0.05. So therefore, there is evidence to suggest that mean molar concentration greater than 0.820. It is a good idea to also report the significance level here. So we can write here at alpha is equal to 0.05. So maybe the exclamation mark may be here. Anyway, and note that this is actually a strong conclusion, because it leads to rejection of the null hypothesis. Now we have reason to believe that H1 is greater than, mu is greater than 0.820. Now, if I would like to determine the p-value, then I'm going to be only using that T0 value, and also with the corresponding 14 degrees of freedom. So actually T0 is being found to be equal to 2.71, and degrees of freedom here is 14. So what we do is we would like to find the T value which satisfy this condition. Probability of T distribution values at 14 degrees of freedom greater than 2.72. So you would like to find the T distribution value, or the tail, right-hand side the tail at 2.72. Unfortunately, T distribution table, as I said earlier, is not that much highly resoluted, so high resolution. So therefore, the best that you can do is to come up with the closest T values. And so the closest T values are, for instance, this one with 14 degrees. It's going to be always on 14 degrees of freedom. This is, let me get rid of the parentheses. If you read from the table, is equal to 2.624, and T 0.005 at 14 degrees of freedom is going to be, of course, a higher value. So note that 2.72 at 14 degrees of freedom lies somewhere between those two, which corresponds to, if this is your T distribution, if this is where 2.72 is our T0 value, since this value is not exactly given in the table, we search for the one with the closest T values at, again, 14 degrees of freedom. And the closest value that we find is this one, 2.6, and this one, 2.97, on the right-hand side and on the left-hand side here. So this one here, let me use another colored pen. This one here is going to correspond to this area. So this 0.005, and this one, the one on the left-hand side, is going to be consisting of a larger area. This is going to be equal to 0.01. Therefore, so formally was just for representing the whole thing. Actually, you can do the whole thing easier in this way. T 0.01, 14 degrees of freedom, 2.642. Our value that we would like to find is T0, which is equal to 2.72, which is smaller than T 0.05, 14 degrees of freedom, which is equal to 2997. Since this is the case here, therefore, P value is going to be between 0.005 0.01. Note that I realized that in the previous years, some students confuse this with a confidence interval that has got nothing to do with confidence interval. P-value actually has an exact value. And for instance, by using MATLAB and by using this value, 2.72, you can find the t-distribution value for 14 degrees of freedom, which corresponds to the tail probability, tail area of the t-distribution with 14 degrees of freedom at 2.72. You can find this value exactly. However, since with the tables you have, since they have, as I said, a limited resolution, this is the best one that you can come up with. And as I repeat again, this has got nothing to do with confidence intervals. All right, now I'm going to be talking about again normal distribution, and this is going to be, should be strictly normal here compared to the previous case where we may use central limit theorem for slightly larger sample sizes. And it is also known that t-distribution is still a pretty much good model even if you have slightly non-normal data. On the other hand, it is pretty much crucial that to be able to estimate variance using chi-square distribution, then you should have a strictly normal distribution. In this case, we would like to conduct a hypothesis test on variance or standard deviation. So this is not that this is the same order that we have followed when we talked about confidence intervals. And we are going to follow the very same strategy since we have already our sample statistic S square when multiplied by n-1, and this is going to be the hypothesized sigma square value. This is going to be our x square, which is going to be chi-square distributed with n-1 degrees of freedom. And probably you can recall the chi-square distribution with different degrees of freedom. So what kind of an hypothesis test can we have here when we would like to test the variance of a normal distribution? It's going to be variance of our process here on the left hand side is going to be equal to a given value. Again, inequality. The alternative hypothesis will be, again, the variance of our process is not equal to that specific value. In this case, at a certain alpha value, again, given a certain alpha value, H0 would be rejected if this test statistic x0 square. And let me repeat what test statistic is. This is sample variance that's going to be obtained from the sample, number of samples minus 1, which correspond to degrees of freedom. And this is going to be the hypothesized value for the variance. So again, we take it for, at least at the beginning, we take it that the H0, the null hypothesis, is true. We continue based on this promise and we check the result. Anyway, if x0 squared comes out to be a high value, very high value, or a very low value, greater, smaller, then we would say that this assumption, taking sigma 0 square for process variance, is invalid. Therefore, variance of the process is not equal to sigma square. Now here we have two, well, just like a pure normal distribution, we have an upper critical value and a lower critical value. But as we covered in confidence intervals, since a chi-square distribution is not symmetric, this upper and lower critical values will not be the negative of the other one. If we recall the t-distribution case, note that this is going to be only a single t alpha over 2 value. We compare the absolute value here because it may be t0 may be greater t alpha over 2n-1, or t0 may be smaller than t alpha over minus t alpha over n-1. So we have an upper and a lower critical value, but note that they are just negative of the other one, this same value. Here, this is not the case due to non-symmetry and also non-negativity of chi-square distribution. So actually, both of these limits will be positive values. So note that this is an estimate of variance, and this is going to be the suggested population variance value. So here we have a ratio, and since they are all squared, they are positive numbers, we multiply this by n minus 1. So if this value, if s square is very much smaller than the hypothesized value, then we are going to have an x square value which is very small. Here maybe, right? It's going to be positive. It's going to be positive, but it's not going to be a large value, and that would mean that the sigma square value that is hypothesized is too much, right? Because this value has come out to be so small. Or it may be vice versa. S square value may be too large compared to sigma square value. In this case, the chi-square random variable may come out to be a large value, right? Then again, you would reject the null hypothesis for both cases. So these two critical values are determined by chi-square alpha over 2 n minus 1 for n minus 1 degrees of freedom for a significance level of alpha over 2. So right-hand side probability is going to be alpha over 2. And the other one, this one is going to be not minus this value, but sigma square 1 minus alpha over 2 n minus 1. 1 minus alpha over 2 means this side, this part probability which goes to infinity is going to be equal to 1 minus alpha over 2. Therefore, the left tail probability, which is going to be 0, which is going to decay at 0, is going to be equal to alpha over 2. So, and when it comes to one-sided case, right, this time they are going to be talking about this side here, then the right-hand side limit will be only considered. Therefore, we are going to be only taking into consideration the upper, the critical value is going to be alpha here. So it's going to be chi-square value alpha at n minus 1, because we are talking about a single side here. Therefore, we don't care about small sample variance values, but if the sample variance is too high, so that it's going to make this x square x0 square term higher compared to this critical value, then we would suggest that the alternative hypothesis holds. Now the p-value, the logic is total the same like t-distribution. We would like to find the chi-square distribution value at n minus 1 such that it's going to be greater than our x0 value. So let's say that this is the chi-square distribution at our n minus 1. From our sample, we have computed our x0 value to be here, x0 square value to be here. We are trying to find this area on this tail. And basically, mathematically, it means that we are trying to find the values here on that chi-square distribution, right, which is greater than x0 square, and we are trying to find the corresponding probability. And this right-hand side probability will be the p-value. The very same logic that we have covered in t-distribution. And when it comes to the case 2b, which is just this alternative hypothesis change direction, it is the very same story, but this time we are interested in this region. Therefore, the significance level is going to be 1 minus alpha here, because it's the right-hand side probability which this notation represents. And the p-value is going to be just the opposite of this slide. It's pretty much obvious and clear. All right. So, as a question. Well, actually, this part is related with the sample, right? So let's leave this part to the end. First, let's deal with the question. In a bottle filling process, again, it's a very typical example I may think of. Volume is normally distributed. That's great. Target variance is 0.010 liters square. All right. But there are complaints about a higher variance in products. Test this hypothesis at 0.05 significance. So the hypothesis test here will be this. Our variance is 0.010 liters square. This is the target value. On the other hand, we have reason to believe that this may be the actual variance may be higher than that one. So before taking any samples, we construct this form of the hypothesis. It's the very first thing. Then now we can find the limit, the upper critical value. It's going to be equal to, it's 0. Since this is a one-sided test, it's 0.01. And note that we are going to conduct this test. We should also decide that we are going to conduct this test with 20 observations, items. So we are going to need the chi-square value at 0.05 significance level with 19 degrees of freedom. And if you read from the textbook is going to be equal to 13.40. All right, we have the hypothesis test, we have the upper critical value. Now we take a sample of 20 specimens. These are X values starting from X1 to X20. I again omit the step with the real values, but I think from now on I'm going to be using real values, and in the assigned questions, they are all, of course, the computations you should do by yourself. And what we only need to do, if we go back, our test statistic actually is comprised of n-1, which where the sample size is n. S square should be computed from the sample, and sigma 0 square is the hypothesized value of the null hypothesis. So it's that much simple. So what we need to compute from this sample is only the corresponding S square value. So S square value has come out to be 0.0153. Note that this is again greater than the null hypothesis. So the question is that the sample variance being greater than the hypothesized value, whether this value is significantly large so that we can deem this discrepancy or the deviation from the positive deviation from the hypothesized value as a possible explanation. Can we say that variance is actually not equal to 0.010? I repeat again, is this S square value, is it significantly large compared to the hypothesized value such that we are going to deem the hypothesized value to be wrong, and actually the actual variance is greater than this hypothesized value? All right, so in order to do that, we do this test. So our X square value here, this is the test statistic, is going to be equal to 20 minus 1 multiplied by 0.0153 divided by the hypothesized value, 0.010. So if we do this calculation, the result is 29.07. So now comes the comparison. X0, which is 29.07, is this greater than the upper critical value that we have determined at the given significance level? As you can see, this is not the case. Therefore, we would say there is insufficient evidence to suggest that variance of the let's say liquid heights is different from 0.010 liters square at significance level of 0.04. Now, this way of storytelling may seem boring to you, but actually it shouldn't be. It is how statisticians write their conclusions, and the wording is pretty much important here. Remember the jury case, the distinction between the difference between not guilty and innocent thing. You should be careful that I'm not verifying the null hypothesis. I do not say that I prove that null hypothesis is true, but I say that there is insufficient evidence to suggest that the liquid height is not equal to that value or is different from 0.010 liters square at a given significance level, at the given significance level of 0.05. Note that, contrary to the other questions that we have covered, this is going to be a weak conclusion. Now, one trick, if let's say you are the guy who is responsible from that proposal, alternative hypothesis proposal. Now, after seeing this result, note that if you had changed this 0.05 to 0.010, as I'm going to show in a couple of minutes related to p-value, then this conclusion would have changed into really the null hypothesis would be rejected and H1 would be accepted. If you are that person, can you do this trick? No. I said earlier, I repeat again, none of the points in the hypothesis can be changed once sample is obtained and actually calculate. If you have taken the sample, but if you don't know the values, that's okay. But once you calculate the sample statistic, you cannot change anything in the hypothesis. What do I mean by that? You cannot change this mu0 value. You cannot change this significance level. So once these are, think about, there are two debating parties in controversy about whether H0 or H1 is true. What they do is they decide on these values beforehand, collecting the sample. Once they collect the sample, they obey to this rule. Otherwise, the statistics will not be correct. It's actually more than an ethical question. It has probably some ethical side by changing the agreement here between two parties, but from a scientific and statistical point of view, the statistics will be incorrect. Well, to give you a hint, that type 1 error will not be true anymore. It's going to be meaningless when you change your hypothesis test after seeing the sample statistics. All right, so if you would like to find the p-value here, you may say that, okay, it's 0.05 alpha value, we cannot reject, but what is the p-value, right? The value that we could have used an alpha value to reject the hypothesis, to reject the null hypothesis. So okay, 20. So for p-value, the only thing that we need is that 29.07. So let me write that value before forgetting, 29.07. That was the value that we have found, and the degrees of freedom were equal to 19. So in our textbook, we search for the corresponding x0 chi-square values, which actually is on the left-hand side and on the right-hand side of this sample value at 19 degrees of freedom. So if you do that in your textbook, what you are going to see is chi-square value of 0.10 at 19 degrees of freedom. This is actually equal to 27.20. This is smaller than the sample value I have determined, 0.7, and this is smaller than chi-square value 0.05 at 90 degrees of freedom, which is 13.40. Therefore, my p-value is going to be between 0.10 and 0.05. Now, I expect you to have understood the concept of p-value. If you had done so, you should realize why at a significance level of 0.05, we were not able to reject the null hypothesis. But if this were slightly greater than 0.05, for instance, if this were equal, if the significance level were taken to be equal to 0.010, then we would have rejected the null hypothesis. Please go back to the lecture about the p-value and try to understand the reasoning for that, because p-value is somewhere in between those two. Again, this has got nothing to do with confidence interval. It is only due to the smaller resolution of your chi-square distribution table. Now, the last topic I would like to talk about is test on population proportion. And when I covered this topic in confidence interval, I also called this estimation of the Bernoulli parameter P. So this is going to be a hypothesis test on Bernoulli parameter P, in other words. So this is the definition that we have. We have a random sample size of N taken from a population, and the population proportion of P here represents the success probability. So you may think about a Bernoulli process success probability. Therefore, in our X here would represent, in terms of the random variable, X will represent the number of successes in a sample N. And we actually consider this sample, and the sample statistic will be a function of x here, the number of successes out of sample size n. We are going to consider this to conduct an hypothesis test on the population parameter p here. So basically our hypothesis test, the form of the hypothesis test will be population parameter here p is equal to some presumed value p0, or it's not equal to p0. Note that this is case 1. In the other distributions, I'll talk about case 2a and b, where the alternative hypothesis change into a form of greater than and less than. Here I'm not going to talk about that because it's the same idea here, but we can have again questions related to that, greater or less than. It's the very same logic. So I'm going to just concentrate on this case. So anyway, for this case, note that actually, if you recall from the confidence interval, the assumption that we used was the large sample size, the approximation to a normal distribution assumption for binomial distribution. So if when you have binomial distribution with np0 value greater than 5 and n1 minus p0 value greater than 5, and actually this corresponds to, for most cases, usually a large sample size, because if n is large and if p0 is not very close to 1 or is not very close to 0, these conditions will be automatically satisfied. Anyway, if this is the case, we have shown actually in chapter 4, I guess, or 3, I cannot be sure, that expected value of x is going to be n times p0, which is obvious because it's the expected value of binomial random variable, and the variance is going to be also the binomial random variable variance, but it's interesting that it's going to be approximately normal distributed. So the test statistic that we are going to be using is shown with this standardized normal distributed random variable. Here, when we divide both the numerator and denominator by n, so both sides multiply by 1 over n, then in the denominator, we are going to have x over n. These are number of successes divided over the number of trials, right? Which is going to be a maximum likelihood estimate for Bernoulli distribution parameter p, which we have actually talked about in confidence intervals. So basically, if you just follow this derivation, this quantity would be normal distributed with 0 mean and 1 standard deviation. So basically what we are going to do is, from a sample, we are going to be obtaining this test statistic. Then we are going to compare it with Z alpha over 2 value. If it's greater than Z alpha over 2 value, we are going to reject the null hypothesis and accept the alternative hypothesis. That's the basic thing. And for the other cases, for the other inequalities, you are going to adjust this procedure with the alpha Z, converting Z alpha over Z alpha, and comparison from the right direction. You should adapt it for the other cases. And the p-value is going to be, for this case, is again going to be exactly the same. We are going to find it using the exactly the same method we have found p-value in other cases. So, and simple question. We would like to test whether the average of 3-point shot success percentage of a basketball player is at least 50%. Well, actually, after I have been actually using this question for pretty much long years, but actually I know that this is a stupid question. The reasoning is this: if you would like to test whether the average of 3-point statistics of a certain player, what we do is we can easily find the population mean value or population average, because we usually have all the historical data. So let's make this question more realistic. Let's say that we are talking about a local player and we don't have the statistics for that local player. It's only rumored that there is a very good basketball player playing around, right? And that's only a rumor. And somebody suggests that his 3-shot percent success is at least 50%. So what do? We would like to test this. Now, the testing part is not also very rigorous, but we can make it kind of more realistic, or close to more realistic case. a randomly selected sample of 53 point shots in the last few seasons is selected. Well, actually, if you know all these shots, then you are going to find the population mean value. You don't need to sample them. So we may liken it. Let's say that we have some random videos of that guy or girl who is throwing 3-point shots, and there are random selections of his or her 3-point shots. So we just take these videos and 50 of these videos, and we see that out of these 53-point shots, 23 of them are success. And we would like to test this hypothesis here using this sample. So first of all, without having any information about that part here, except that n is equal to 50 is going to be known. Sample size is to be known. Actually, as I said earlier, as I mentioned earlier, that sample size is usually determined, of course, should be determined before taking the samples, but is usually determined taking the power of the test into consideration, which we are not going to consider. And if you recall, power of the test is related with type 2 error. And we would like to conduct a certain test with a certain power. What should be the sample size is the first question, but that's a topic I'm not going to go into. And usually a certain size is determined, sample size. Then using that sample size, the test sample is collected. Anyway, so first of all, what we should do is, since this calculation here, this formulation is based on normal distribution approximation, we would like to check whether this condition is satisfied. Let's convert this question first of all into an hypothesis test. Then we are going to solve the rest. We are going to see whether the normal distribution approximation holds or not. Now, converting this question to the hypothesis test, I think, is the most interesting point here, because here the wording "at least" or the phrase "at least" is used. And as you can see, the null hypothesis or the alternative hypothesis may not seem that much straightforward. If you are watching this video for the first time, I recommend you to pause here and try to come up with your own hypothesis test scenario. What's the null hypothesis here and alternative hypothesis here? So, well, I think the easiest way to talk about this is first write the hypothesis test in H0 in H1, then talk about it. Well, this is going to be the hypothesis test. P is going to be equal to population proportion, Bernoulli distribution parameter. P is equal to 0.50, or P is smaller than 0.50. Now, why did I write it that way when it comes when we have at least statement, and which hypothesis corresponds to which statement? Now, believe it or not, this statement will include or will correspond to this guy voicing this at least statement. So there was at the very beginning, I said that actually this hypothesis test divides the whole real axis into two for the possible values of the population parameter. Since this says P is smaller than probability smaller than 0.50, this actually means probability is greater equal 0.50. But we always use an equality, and I think now it's easy to explain why we use an equality, because in the hypothesis that in the statistic, we use, instead of mu, we use that equality value, 0.50. So we assume that this is the reference distribution, null hypothesis. Therefore, it should be an equality. But actually, in this question, there is the hidden or inherent hypothesis that P is also maybe greater than 0.50. So this at least statement corresponds to this part. You may say, why did I use at least statement in the null hypothesis? Because at least means 50 is included. So if it's exactly 50, although it is not possible for a real for a continuous distribution parameter to be equal to exactly to a specific value. On the other hand, if when we use the at least statement, logically it means we also include 0.50, and including a specific value means that that value may be equal to that value. Therefore, equality should be in the null hypothesis. So therefore, the alternative hypothesis turns out to be equal to the probability or the proportion being less than 0.50. For instance, if this were, instead of at least, is not more than or not is not as high as 50%. If this were the case, then I would take this hypothesis if on the other hand, if instead of at least, this said more than 50%. Note that there is only a very slight difference between at least 50% and more than 50%. That's a very subtle thing, but that makes the whole architecture of the hypothesis test different. In this case, this would be the novel or the bold suggestion, and that would be put in the alternative hypothesis. So if this were the statement were more than 50%, then the null hypothesis would be again 50%, but this would include also smaller than here. So that would be P greater than 0.50 would correspond to the suggestion of that guy. The percentage, success percentage is more than 50%. On the other hand, when you say at least, then you include 0.50 here, and then you are reserved for the null hypothesis here. And that's actually an interesting point. If in the commercials, actually, if you have seen that at least kind of statements are usually used, not more than is used. Because when you use at least statement, you reserve your hypothesis for the null hypothesis. So if somebody does not believe you, he or she who does not believe you have to prove that your statement is incorrect. On the other hand, if you say more than 50%, you leave equality to the null hypothesis, and you yourself should show that your statement is valid. So that's an interesting point. If you haven't understood, please think about it and listen to this whole thing again. And probably in the assigned questions, there are a couple of questions involved in this issue. Anyway, so let me write the whole thing again. H0 is probability is 0.50 and H1 is probability is smaller than 0.50. So we are going to conduct the test at alpha is 0.025. So this is our hypothesis test. All right, the very first thing that we are going to do is we are going to check whether the normality assumption will be valid. So it's going to be 50 times. Note that we do not know the exact values, of course, known, but we are going to be using the hypothesized value of probability, which is equal to 0.50. And this is equal to 25 greater than 5. 1 minus 0.50 is also 0.50. So it's going to be again 25. So anyway, let's find the Z value here. So normal approximation, let's write it. Normal approximation is valid. We'll come to that in a minute. Let's find the Z value. Since this is a smaller than kind of test, we need the left-hand side critical value. So we need the value of Z 0.025. This is a one-sided test here. The negative Z minus 25 value. This is going to be minus 1.96. So we have our lower critical value also. That's great. Now let's compute the test statistics. Z0 is going to be equal to 23 out of 50. If we go back here, the test statistic is the maximum likelihood estimator of the Bernoulli distributed P minus the hypothesized value divided by this standard deviation term P0 minus 1 minus P0 over F. So it's going to be, excuse me, equal to 0.46, which is 23 over, right here, 23 over 50, which is P hat, and this is 0.46, minus the hypothesized value is minus 0.40 divided by square root of minus 0.40, p times 1 minus 0.40 divided by number of trials, which is 50. Let me check. Yes. And the result is minus 566. Now what we do is we check those two values. We check whether set 0 value, which is equal to minus 566, is smaller than the critical z value, which is equal to minus 1.96. No, it is inside the acceptance region. That's when we say there is not substantial evidence to show that her 3-point average is less than, again, I have to be careful with the wording, less than 50%. That is one of the statistical, that is one of the conclusions that you may write using the statistical terms and also the statistical logic we have used here. But note that this is a weak conclusion. Or you may say alternatively here, you could have said, we cannot reject that is her 3-point average is at least 50% at alpha is equal to 0.025. Again, another weak conclusion and a statistically valid statement. We cannot reject that her 3-point average is at least 50%. There is no substantial evidence to show that. Yeah, I have also written the other statement. I cannot think of any other way. There may be other ways of writing, but it's going to be explaining or saying the same thing from different perspectives. And when it comes to p-value, we are just going to be using the normal distribution here. P-value here is going to be simply equal to the cumulative distribution function of normal distribution evaluated at 0.57, this value. We are finding the area on the left-hand side, on the left cell, and this is going to be equal to 0.28. So the p-value is equal to about 28%, which is a pretty much high value, which means that the null hypothesis may be true, is likely to be not which says that, I'm sorry, not true, but which says that it is not easy to reject the null hypothesis. Note that, again, let's look from a bird's eye point of view. P is suggested to be 0.50 or even greater than that, at least 0.50 here, although the sample mean is found out to be equal to 0.46. So this one is lower than that value. On the other hand, I still cannot accept H1. So you may ask why this is the case, but these are mathematical calculations and statistical reason. But the philosophy is because we deem this deviation actually the lower value, lower sample value lower than the hypothesized one, we deem this to random, to sampling fluctuations or sampling variance. So from sample to sample, due to the variance in the samples which are reflected in sample mean, there are going to be deviations. So we deem this difference to be born out of this sampling variance, not due to the incorrectness of the null hypothesis. So that's all I'm going to talk about chapter 9.